Afternoon. The first speaker is Fabricio Souza from Federal University of Uberlândia. And Fabricio.
Okay, thank you. I'd like to thank the organizer for this nice opportunity to be here in Natal, deliver this talk. So I talk today about quantum dynamics and entanglement with semiconductor quantum dots. Okay, this is the very beginning of the semiconductor technology. It is the first transistor developed using germanium. It was done in 1947 by Bardeen, Brett, and Shockley, and they received the Nobel Prize for that. After that, the computer technology started to grow up. This is the first computer using transistor, the first radio using transistor. And after that, the technology has improved quite a lot. And as you can see in this scale, nowadays, it's possible to develop transistors. This is a picture from the Intel site. You can see this is a very small transistor, basically of the size of a virus. Okay, so you have here the virus of influenza. It's around 100 nanometers, and here you have an Intel transistor of the same size. Okay, so nowadays it's possible to build up in a lab very small devices, even smaller than that. Nowadays you can find the transistors in the range of 10 nanometer or even smaller. Okay. This made it possible to keep alive the Moore's law that says that the number of transistors incorporated in a chip will approximately double every 24 months. So when you make a plot like that, you see that it has an exponential increase. Okay, so nowadays you have almost 3 billion transistors in a single chip in the computer. Okay. So people are growing transistors smaller and smaller every day. And this is a very nice single electron transistor, okay, developed using semiconductor junction. They put metal contacts on top of it, and they can isolate a single electron inside this region here. Okay, so it behaves like an artificial atom that you can control its size, the space between levels, and so on. And this is a good device to build up quantum technology. Okay, and this is the first proposal to use quantum dots for quantum computation. This is done by Loz and DiVincenzo. Okay, they show that it's possible to perform logical gates and playing with the exchange coupling between single spins in each quantum dot. And why can you describe the charged quantum dots? Okay, so let's say that I have two quantum dots here, and I couple to the quantum dots electrodes, which means that we can have, for instance, two semiconductor quantum dots coupled to some metallic reservoir. And these reservoirs can provide electrons to the system or drain electrons from the system. Okay, like here, you can have a single electron jump into the quantum dot, perform some tunneling between the dots, and then leaving the quantum dots. So while the electron is inside this artificial molecule, because when you have two quantum dots close to each other, we are basically have an artificial molecule, okay? While this electron is inside this artificial molecule, you can perform some quantum manipulation there, right? So, and this kind of system permits you to initialize the system in some specific quantum state, reading it, and allow it to evolve in a quantum description when it's, let's say, closed, okay? And you can also use it in hybrid setups, including superconductors, like here. You can have two quantum dots coupled to a superconductor lead. So let's say that you have aluminum there, and you decrease temperature to 10 Kelvin, let's say. Then you go to the superconductor phase, and then you can have some dynamics here using Cooper pairs. The Cooper pairs can be split in two quantum dots, okay? And you can look, for instance, how they become entangled when they are split, one in each quantum dot. Or you can use carbon nanotubes as a platform to build up quantum dots. You can use gates, like gold gates here, to define semiconductor quantum dots inside the carbon nanotubes. We will explore these both systems in order to see how it can be used for quantum computation. Okay. So for that, we first developed fermionic formalism, because this kind of system is mainly the dynamics is given by electron. So you have fermions particle, and we developed formalism to describe these dynamics, including source and drain of particles. And for instance, let's say that we have a system here composed of an arbitrary number of quantum dots or levels, and this system is attached to many reservoirs. So you can have, for instance, reservoir 1 can behave like a source of particles, reservoir N can operate as a source of particles, so you can have a current flowing in this system. Okay, so you have an open system out of equilibrium, right? So in order to describe that, we should remember to use these anti-commutation rules, because now we are dealing with fermionic particles, right? And we expand each state of the system in terms of Jordan-Wigner decomposition. Okay? We write, let's say, this dm operator is the annihilation operator of state M in this system. It can be expanded in a very general way in terms of Pauli matrices. When you do that, we end up with a formalism that allows you to describe a system like this. Suppose that we have a molecule composed of 4 quantum dots, okay? The dots 1 and 2 operate as 1 qubit, and dot 3 and 4 operate as a second qubit, right? So let's say that we have a single electron in this molecule here, composed of dots 1 and 2, and another single electron in this second molecule, composed of dots 3 and 4. Somehow we injected particles there using reservoirs, okay? So you can use a reservoir to inject an electron in dot 1, and a reservoir to inject electrons dot 4, and put the system to evolve in time, okay? But you should, in principle, measure that. And how can we measure a charge in a single electron transistor? We can use this quantum point contact, okay? This is a system like that, which is a very localized level, okay, coupled to source and drain. And we use this level 5 here to mimic this quantum point contact, okay? So let's suppose, for instance, that dot 1 is occupied by 1 electron. When an electron coming from the source to the drain in the probe try to pass through level 5, it will feel dot 1, it will feel that dot 1 is occupied, which basically it's called Coulomb blockage. Okay? If dot 1 is occupied, dot 5, the electrons coming from the source cannot have enough energy to pass through this quantum point contact. Okay? Otherwise, if it goes through the quantum point contact, means that dot 1 is empty, something like that, right? So when you initialize this system, let's say in the configuration 1001, and put these systems to evolve in time, we see that the concurrence that basically measures the degree of entanglement of this 2-qubit system shows an interesting dynamics, which gets close to 1 from the beginning, but then it suddenly goes to 0, and the revival at some point later goes to 0 once again, revival, and finally it vanishes at all, meaning that the probe, the quantum point contacts, basically will destroy the entanglement if you keep on measuring it as time evolves, okay? And also the entropy shows an increasing as time evolves. Now, let's move on to carbon nanotubes. Carbon nanotubes is one of the most clever systems nowadays. You can do many, many things with that, okay? And this is an illustration of a carbon nanotube, and this is the human hair here, and here this is the carbon nanotubes, just to have a notion of the dimension of it, okay? This diameter is of the size of tens of nanometers, okay? So you can play a lot with carbon nanotubes. For instance, you can put a carbon nanotube between a source and the drain of particles, fermionic particles, and the gates below it. And using these gates, you can define localized levels that behave as quantum dots, okay? And you can make many of them in a single quantum dot, right? Like here. Here, in principle, you can make 1, 2, 3, 4 quantum dots along the carbon nanotube. Also, you can build geometries like that. 2 nanotubes in parallel, okay? So you start to think, okay, maybe I can define some qubits in each quantum dot, in each carbon nanotube, and put them close enough to interact and see how it evolves, and if it can generate some Bell states in the nanotube, right? Here is an illustration of a nanotube coupled to source and drain. Okay, so you can, in principle, use the source to initialize your system in one specific configuration, electronic configuration. Okay, so there is some problem there. But anyway, here we have one nanotube with 2 quantum dots defined there. And here below, we have also a second nanotube parallel to the first one with 2 quantum dots. They are close enough to allow one electron, let's say, in this nanotube, in quantum dot 1, to tunnel to quantum dot 2 in the second carbon nanotube. In a similar way, the dots 3 and 4 can be coupled by hopping, okay? The point is that the pi orbital in the carbon nanotube is perpendicular to its surface, so they can overlap with a parallel carbon nanotube, and you can have this nice hopping between them, right? So let's say that this pair of quantum dots, 1 and 2, will be our first qubit, while dots 3 and 4 provides our second qubit. Okay, but there is one nice feature here. Carbon nanotubes has many vibrational modes. Okay, for instance, if you have a single nanotube between two electrodes, they can vibrate like that. Okay, in the range of hundreds of megahertz, and it is quite useful for telecommunication because it's in the range of telecommunication, and the people are trying to build up nanoradios using this kind of vibrational mode. You can also have this radial breathing mode of the... Sorry? They should be close enough to allow this hopping in the range of 1 nanometer, this range. Okay. So, and you also have this breathing mode of the nanotube. So the tube will be like that, okay, vibrating along the radial direction. So it's in high energy. And the nice point is that when one electron is inside the nanotube, it will be coupled to these vibrational modes. Okay, so you have some sort of electron funnel coupling in the nanotube. And our idea is to use this coupling to generate quantum entanglement. Okay, so we can describe the coupling between electronic degrees of freedom to vibrational degrees of freedom using this sort of Hamiltonian here, okay, and performing the Lange-Firsoff unitary transformation, which is very standard in this kind of interaction. Yeah, we end up with this simple Hamiltonian where we have this V effective. This V effective is a Coulomb-like interaction, but with opposite sign. It's mediated by the vibrational mode of the carbon nanotube. So electrons in dot 1 and 3, they will be attracted due to the coupling with this vibrational mode. Okay, this is behind to the Cooper pair formation in superconductors. Okay, if you go to the BCS theory, you see that two electrons are attached to each other via vibrational modes of the LEDs. Here we have a similar effect. Okay, so how this effective interaction mediated by phonons can generate quantum entanglement? Okay. Let's say that we initialize our system in this configuration 1001, meaning that dot 1 is occupied, dot 2 is empty, dot 3 is empty, and dot 4 is occupied. This means that at some point, electrons coming from a source jump into dot 1, and electrons coming from a source jumps into dot 4, and you have this initial state there with 0 phonons. Here we have the modes and the states of the phonons, and we assume that it's without phonons from the very beginning. Okay. So as time evolves due to this effective interaction mediated by vibrational modes, we see that the entanglement of the system, here is the concurrence against time, the first plot. You see that the concurrence increase from 0 to 1. This means that this effective interaction between electrons mediated by phonons provides Bell states, okay, for some specific times. So we are showing that we are generating entanglement between, let's say, faraway qubits using this using the vibrational mode of the carbon nanotube. Okay, here we look at the fidelity. So let's say this is the target state here, 1001 plus 0, 1, 1, 0, or 1, 1, 0. Okay, let's phi equal pi over 2. So you can see that the fidelity reaches very close, a value very close to 1. Okay, so we are found also they state that the system is evolving too, right? And the nice thing is that it is, in principle, a long-range interaction. Okay, if you have Coulomb interaction to couple these two qubits, it should be close. But if it's a vibrational mode, in principle, you have a longer range, and you can have these two qubits being entangled due to this radial Bruffin mode. Okay, how about the Cooper pair splitter? Here in this illustration, we have a superconductor with a Cooper pair up-down, okay, and the electrons can jump to the lateral quantum dots here and there, okay. This is the geometry, and this is the schematic illustration of the system. Additionally, we also shine light on one of the quantum dots. Okay, we put a laser field here, okay, and what happens is that the laser field dress the states of the quantum dot. Okay, when it is dressed, the system level is split, generating ATD, Alterton's doublet. Okay, and we show here that we can probe the Alterton's doublet using quantum transport. Okay, in general, people show that using optical experiments. Now we are proposing to measure it using electric current measurements on that. Okay, so we have here a Cooper pair. They can be split to dot 1 and dot 2. There is also in dot 1 a valence band, and you can promote electrons from the valence band to the conduction band, and in order to dress this state here. Okay, when we calculate the current using density matrix formulas, we show the following. Here we have the tuning. This delta means that the level in quantum dot 2, we can move this level up down here using a gate. Okay, close. You can put an electronic gate very close to this quantum dot 2, apply a gate voltage, and shift this level up or down. Okay, so this is what we are doing here. We are changing this level 2 here. Okay, and this is time. The horizontal axis is time. So let's see. This is the case here. Let's look at this case here. We are seeing that for two specific detonings of the level of the second quantum dot, we see that the current is enhanced and keep alive as time evolves. So in the stationary regime, we end up with 2 peaks of the current for this particular detoning, when detoning is equal omega. Okay, omega is basically omega gives you the optical coupling between valence and the conduction band, as you can see in this term of the Hamiltonian, right? This omega here is proportional to the laser intensity. So when this dot level is aligned with one of the Alterton's doublet, you have a finite current, okay? The mechanism behind that is what we call crossed undriven reflection, okay? Let's say that if you have a superconductor here with, and you have, this is the 0 level, okay, the Fermi energy of the superconductor. And then you have a Cooper pair, here you have dot 1, and here you have dot 2. Okay, they can be split, conserving energy, right? So this basically generate, this mechanism is called the cross-centric reflection, and this is the source of current in this system. So we have current flow in this system, which means that electrons, in the right side, we see that electrons are being injected. Actually, the mechanism is like that. Here is the reservoir. Electrons actually are being injected now from here. And here we are pumping electrons with a laser. Okay. When one electron is in this quantum dot and another electron is this other quantum dot, they interact and form a Cooper pair in the superconductor. And this current, and this, how can we see that? We can look at the current in this right reservoir or the left reservoir, doesn't matter, in the stationary regime, and we can measure the current to detect this sort of effect. Okay. In the left side, we have the opposite. The right reservoir operates as a drain, which means that this is the Fermi level. The Fermi level is very low in energy. So electrons in the superconductor jump to the dots. This electron, when arrived in the dot, can jump to the drain of particles, to the right reservoir, okay? And the other electron remains locked there, okay? And you cannot have an additional cross-centric reflection process, because whenever one electron is in quantum dot 1, it blocks other electrons to go there, okay? You can have Coulomb blockage or Pauli blockage here, which provides additional Cooper pair split. So this is why the current in the stationary regime goes to 0, right? Here you have the left current, which means the current in this side of the junction. You can see a very fast oscillations, which is characteristic of Rabi oscillations there. Okay, when you couple using optical fields, the valence and the conduction band, you introduce in Rabi oscillations, and this is what you see in this left side current of the junction. Okay, you can also observe it in the right side, the Rabi oscillations, but the more relevant effect is the stationary current due to two things: the cross-centric reflection and the laser, the optical field. Okay, if you turn off optical field, you also kill the current. So this is a sort of photocurrent. Okay, this is a photocurrent via superconductor. The current goes into the dot, and then it goes to the superconductor, right? So we have a supercurrent in the middle of the junction. Okay, so maybe I'm almost finished. 1 minute. Oh, so it's perfect. Okay, I would like also to thank my collaborators. Liliana Sanz from Universidade Federal de Uberlândia, Gineton Diniz from Universidade Federal de Jataí, my former PhD student Marisaura Assunção, now she's a professor in Federal de Jataí, PhD student Patricia, and the undergraduate student José. So the final remarks are that we can use quantum dots in carbon nanotubes to to perform to build up Bell states using this effective interaction, okay, between electron-electron, mediated by the electron-boson interaction, okay, in the nanotubes. And we also present an alternative way to probe the Alderton's doublet using quantum transport experiments, okay, which is relatively simple with nowadays technologies in quantum dot semiconductors. Right, so 0, 0, okay. So thank you very much.
Questions?